talks by François Ledrappier and Pablo Lessa, and now Pablo will give this lecture, the first one. You have another one after by Pablo.
Okay, thank you. Thank you, Pepe. Okay, so the idea for this hour is to give some applications of the exact dimensional measures to and also representations. So let's start with an example. One example. So the first example I'm going to give is in SL2. There's a well-known construction which is the following. First, maybe I'll draw the picture. We're going to take closed intervals. Let's call them R1, R2, A1, A2. We have family, RI, AI, disjoint closed interval. In projective space, R2, which would be this circle here. And we take gamma 1, gamma 2, let's say, which we're going to do this. One. Gamma I 2R with gamma I of x minus R greater than I. Gamma I minus 1 x minus so A is for attractor, R is for repeller, and you can pick any number of these intervals, disjoint, and do this construction. Okay. And the generated group. Oh, generated group. Gamma is a free group. It's a very simple group, and it's pretty clear from the picture that you get some sets, you get lambda gamma, limit set, which is the smallest closed invariant gamma invariant. And so this is a really old example, but the natural question to ask, you have this counter set which appears there, and you want to know what its dimension is, and there, you know, I mean, it's super well known. Is this here by Bowen or Patterson? So there are several. I want to mention this from the 7, which says that you know the Hausdorff dimension of the set. And its dimension is the critical exponent of so we're going to sum over all the elements of the group, and we're going to look at the norm of the element to the minus 2x. And so for certain s, this is going to converge if s is very large, and for certain s too small, it's going to diverge. The number is equal to 0. And the critical parameter is the dimension. So that's the the Madison. So now, as the first example of and also representation, which is towards the delivery of the title, so you can do the following. Yeah, yeah, just the operator only. Okay. So, all right. So our first example of an also representation is perturbed the matrix 3 by 3 matrix. It's going to be gamma I 0, 0, 1, 0, 2. Okay, so you have your Schottky group. You put it into R3, preserving a plane. Schottky group times the identity. You perturb it slightly. In the generated group, what 3R is an analysis group which is defined. So what it is you're putting a free group from 2 generators, maybe if I do like the picture, it could be more. You're putting it into SL3R. And because of the nature of the matrices you pick, it's clear that there is some, for each of these elements, if you take a high power, you're contracting most of the flag toward a particular. Okay. So this is my example. Let's look at this. And now I'll give you the definition. If you have any questions about it. Okay, so what's an analysis representation? It's the following: you have gamma, finitely generated group. For example, the free group of 2 generators. And roll from gamma to SL3 representation. So just the morphism. Please, and also. Okay. And here, there it is. Some constant C puzzle. What's that? Write something about it. Okay, what it's about. And this, okay, what am I writing here? These are the singular values. And this is the word length. Okay. So in the example, what I'm claiming is that if I construct this thing by perturbing slightly, then if I take a long word in gamma 1, gamma 2, and cancel out all the obvious things, so anytime gamma 1 is followed by its inverse, I cancel. When I look at the reduced word, how many elements it has followed by, that's the word length. And the singular value, the biggest one is just the norm of the matrix. And the second one, I'll give you a picture now. It's saying that they're really separated, they're exponentially separated if the word is very long. Singular values are just this thing here. You take here when it's 1 and R3, you apply a matrix G, you're going to get the ellipsoid. This ellipsoid has three semi-axes, different length. In this one, its measure is +1 of G, which is just a norm. This one, its measure is +3 of G, which is just the norm of the inverse. And then the middle one, the easiest way to say what it is just it's 1 over the other two. It's matrix for the determinant one. And it's 1 times S2. Okay. Those are the three finger bounds. That's the definition of the dimensional subgroup. And I can't stress how, I don't know, as far as I started learning this not that long ago. But it seems to me that to get to the definition, like you took a really strong review to get this definition. And I should mention, I should just mention this. Can't be like an exact timeline, but I would say it starts with Hitchin. We're studying representations of surface groups. This is the 9s. We 2000s. And then there's at least three more groups of people who study the construction of European there. And I should mention that I should say that a couple of very long environment and papers from the 2010s are what more or less allow me to say this. Okay, so what happens with when you have one of these? So what I'm going to say now is that when you have one of these also representations like this one, you also have an actual set lambda gamma with place of flat. Okay, and what should it be? And there's several ways to say it. I'm confused. Yes. Oh, okay. Maybe this. So, right. And what's the limit set? Is what I have to say. Limit set. So, whenever you have the three singular values different, but whenever like S1 rho gamma, it's actually different from a single one. Whenever you have this situation, you want to read different singular values. There's a well-defined phi 1 gamma, the most contracted line to 0 in my 3. Phi 2 gamma, most contracted plane. Phi gamma, phi 1. The most contracted. flat. Okay. So what is it? If you look at the two smallest outliers that ellipse over there, the image of the smallest one gives you the most compacted line, and the image of the plane containing both of them gives you the most compacted line. And what's the limit set? Lambda gamma. It's all limits of the form word length of gamma n goes to infinity. And I look at psi of gamma n. And it's what you would think when you look at this Schottky type thing. It's, you look at all the attractive flags, which are also the repellers are attracted to the inverse. So, and you look at the closure of that, and that's my limit set. And the natural question is, what is this house of dimension? So, any questions so far? Or the flag is parallel. So, yeah, the flag is the pair of both. It's Taiwan, comma, like included. Similar value decomposition, you get it. So the plane minimizing the determinant is actually contains the line minimizing. No. You can find for the station it's the same thing for Luca. So, but if you go into SLER, you can consider different types of for each set of public vectors. You can consider I don't have to when in the house. So, usually the most common is first so you want more than there what you get is a line. But in SL3, having the first gap, which is what I wrote, is equivalent to having the second gap as well. I could write that the S2 over S3 is also very big, but it's here there's just one type of analysis. All the possible limits of the most effective. So all possible limits of psi gamma n when the word length of gamma n goes to infinity. So you do the combination, you would move it over there and you go to something. That's a very nice question. Actually, a theorem or a logic of this line that I do. Yeah, if it makes this, so that's what I'm saying. There was not, so these are at least 3 page papers about the definition. There are several problems. If you consider a value, the value, all sorts of one of them was graph that the group is automatically. All right. And now I think I do. Are the same? Well, you don't get all the time line plane and flag, right? But here it's not an issue because it's only an issue for word length, which is small. Because once the word length is large enough, we'll be in the situation. But except for a finite set, you always have a word. And the point is we're really okay. So there's it's a really nice paper. There are several things, but this one you can get kind of a invariant tones, invariant multi-tones like program. Any more questions? Yes. Yeah, that's fine. Yeah, I think it's the same. I'm not 100% together. So there's some discussion also the complement of the largest open set where you actually treat the section. There are some topologies, but I think in this case they can work. All right, so there are plenty of these groups. One construction is to do this, and there's another one I'll talk about later, if time permits. And 20 minutes, stuff like that. And so we want to say something about that question. Okay? Also dimension of these sets. So our approach is to construct a random walk on gamma. And look at a stationary measure. The stationary measure will be supported on this. Okay. And so it gives you a lower bound for the health estimate. So of course, our first application will be an upper bound for health estimate. I don't think I can exaggerate how excited I am about this result. I don't. It's a shame to erase the Schottky groups, but. Oh, I should mention this question of the Bowen, Patterson, Sullivan theorem. I think it's still pretty interesting if you consider infinite generated Schottky groups. There's lots of not that much work, but there is some work. François and Pablo have a paper, and there's some paper with Admissible, and there's some. It's not clear exactly what happens if you do an infinitely generated Schottky group. Bizarre behavior. So even for SL2, it's not dead. So what was I going to do? Oh yeah, random walk. Random walk. We want to do a random walk. I'm going to use the wet one to erase. Random walk. Okay. So the first thing I will say is this from Mary's question, which is that I'm just going to say that the gamma is hyperbolic. Word hyperbolic. And I really don't want to discuss, I mean, we could give a 1-hour lecture about the definition of word hyperbolic group. So the free group is an example. And when you look at the Cayley graph, which is the elements of the group are vertices, and you join them, they differ by one generator. When you look at the Cayley graph, it's a tree. And word hyperbolic means it's tree-like. And the formal definition is that the triangles are thin. So if you have a geometric triangle, and for these types of things, I mean, normal this definition to success, you get a well-defined boundary, this thing, which in the case of the tree would be just the ends of the tree. So the infinite reduced words would be the boundary. And okay, so if we take M, the don't say something more before this. Oh wait, yeah, I do want to say something more. So and the maps psi1, psi2, and step up. And the psi, it extends to the boundary. Extends to the boundary. Very nice property, continuously. So I don't want to say much about this. Just think about the free group, and you have a well-defined flag for each way of going to infinity and the tree. And all right, so now we do a random walk. Maybe I should say one more thing. Hold on one. Adding more things to the thing. If X and Y are different, then the flag associated to X and the flag associated to Y are in general groups. That took up more space than I thought. But X and Y are in the boundary. So let's see about the random walks. So the point is that we're going to construct a measure on the limit set, and the way to do it is you walk randomly on gamma, and if you walk randomly on the free group, usually you end up getting a very long word, so the word length goes to infinity. So you're going to an end in this, you're going to a boundary point in this group. What you do is you look at the probability of the boundary that this gives you, probability of getting in certain parts of the boundary, and you push it by this map, this basic map. And that gives you a stationary measure on the limit. So the dimension of that measure, a priori, is the lower bound for the whole dimension. Okay, so that's the plan. To do this, I already wrote and the walks, so I didn't say anything about it. What you're going to do is you're going to take M probabilities on gamma. With finite for small word length as a mean. And so this is the semi-group generated by the support. I could say semi. Non-elementary, which I'm going to say. What it means in the free group is that it's not just powers of one element. You have two independent. Also don't feel it. So two independent translations. So most measures have this property, not this one. And for each of these, I'm going to say maybe a theorem. This is essentially Furstenberg, but it's really, really nice. You look at this paper by Meyer and Thielsen, which is called Random Walks on Weakly Hyperbolic Groups. There, this is stated explicitly, and they're very nice proofs. A bit more general setting, but it's nice. It's nicer than trying to get the techniques from some other group. So the theorem is there exists if mu is one of these measures, then there exists a unique mu on the boundary, which is mu station. And this is exactly the description I was giving of you start multiplying elements chosen at random with probability mu, and you will eventually this random element that you're constructing will go very far away and will converge to a point in the boundary. And mu tells you what's the probability that this point will end up in a certain set or some other. So that's the theorem. And the measures we want to construct on the limit set and on its projections with the many of lines and planes are we have on and projections the projected space of our free and the rest one two-dimensional subspace. So we have these three measures, and François has been talking for the first half of this course about how these measures are exact dimensional. Okay. We have these three measures, and we know that they're less dimensional, and we have a pretty weird formula for the dimension. So, yes. Yeah. Yeah, so you take basically if it's a free group, which is the only example I gave so far, you start picking any when it's the board at random, multiply it, and usually the word gets longer and longer. So the word length for infinity, the means there's convergence, the sum infinity reduced forward. This is exactly the boundary. Yes, more general fact of what happens on the group. Everything we have the wall. This will happen unless the semi-group generated by our measure is very small, the powers of one. And you think of the entire regular. Could I have a unique secondary measure? Oh, it's sorry, this thing means unique. Oh yeah, it changes it a lot. It will change, and it's really a subtle issue to know how it changes. Because okay. Right. The mu you only know it implicitly by this equation of stationarity. On average, if I get I with the elements of gamma, an average with mu, and I get mu again. So you have to analyze how the solution to this equation varies. You have a mu and it's depending on what setting you're in. Oh. No. You can always change. There's examples where it's good to be known. Best one is for the free group. If we measure mu support on the generator, we get the concept. And we get the formula. And then for finite support, there's some more we can do something for this. The good thing is we don't care about that. Okay, so now let's see what the dimension of these measures tells us. Taking a long time. So the first thing is the first convergence. It plays a role in the formula of François. I don't care if you know what it is, but so the thing that's surprising here is that this map psi, because of the property that psi x and psi y are in general position, in particular, it's injected. Okay, so you don't get extra information from knowing in terms of some bijection to know like the point on the boundary, the line, or the plane associated. So what that implies is that you get the same entropy. Right now, this is just some positive number. You get the same entropy if you do first number entropy for the pair mu and mu from the boundary. You do the first number entropy for the pair. You push forward to the space of flags. Or if you do the first number entropy, so push forward to the space of lines, or push forward to the space of flags. All right? We have the same thing. And we don't really care, okay, the first number entropy is mysterious, but we don't really care. What we care is that we have some formulas, which I will now write, which tell us that these numbers play a role in the dimension of these measures. And I'll now tell you what the formula is. This is what François was talking about, is that dimension. have these dynamical formulas, which tells us the following. The dimension of the measure you get on the space of flat. What we know, I know that yesterday many people freaked out with the diagrams, but you get a formula, and the formula is some positive numbers. I13 of n divided by this. I12 of n divided by 2 divided by 3. And the guys are the Oseledets exponents for the random walk with when you do rule of mu. So you push mu to the less of 3r. You do your random walk and the 3r, you get exponent. So that's the first one. Okay, and what happens is that these guys add up to kappa. Okay, the numerator. And furthermore, each term is less than or equal to 1 because each term is the dimension of something. You know, on a fiber of dimension 1. One of the gamma i's that's proposed right here. I'll write that in a second. But what do we get for the lines? We get that the measure on projective space is also at that dimension. So our formula is that you get some number, let's say kappa 1, 3 in the lines. So I put an L on top. And then you get kappa 1, 2. And these numerators, they also add up to kappa, same number. Okay. And finally, the measure on the space of planes the formula you get, hopefully the next problem can explain a bit more where these terms come from, but what you get is this. What do we know about the terms? We know the following. Each term. I should write it in four. Yes, all of them add up to kappa. I'm going to try to say that right now. Okay. So what do we know about these numbers? Each term. So it's very, very hard to understand each kappa ij. But what we do know is that each of these guys, kappa ij, something, okay, is non-negative. It's less than chi I minus chi j. And we also know that the sums of the kappa ij are kappa, the same kappa that is. Okay. Those are things that come out of the analysis of how to explain. Okay. So this is we're using the theorem of the black box. What does the exact dimension theorem give us? It gives us formulas for the dimension of these three measures. But the special property of the anosal representation is that because that map is injected to the projective space, to the planes, and to the flags, we get the same entropy all three times. In general, we would get two things. So what does this tell us? You get that kappa, in particular, if we look at the second and third formula, it's going to be less than or equal to chi1 minus chi3 plus the minimum of chi1 minus chi2 and chi2 minus. Okay. But what does that imply? So where did I get this? I look at, since each term is less than one, the sum of the kappas in the formula for P will be less than the sum of the denominator. Okay. Same thing for the second formula. And if I do a minimum of those two, they're the same sum, I get this. But then when I plug this quantity into the first formula, I know the numerators add up to this quantity kappa. I get an upper bound for the dimension. These measures on the paper flat. So the theorem is what is the upper bound? The dimension of the stationary measure on the space of flags is less than or equal to. Okay, you have to divide chi1 minus chi3 plus this minimum into the three numerators in the first line and try to get the largest number possible. And what you're going to get at maximum is 2.5. So the chi1 minus chi3, you split it up into the second and third terms, get 1 plus 1, and then this minimum is going to be less than half of the sum of the first element. So we get 2.5. Of course, we said with François when we saw this, this is kind of crazy. We said, okay, what's happening is that the maximum possible Hausdorff dimension of a limit set of an Hausdorff representation in complete is 2.5. Okay. But there's I'm tricking you because you don't know that the dimension of this set is actually realized as the dimension of some measure. Okay. But then, so I was asking and saying, okay, maybe we can try to prove. Yes. Yeah. Oh yeah, lower bound. So this one is more exciting to me. So I'm talking about this one first. But the lower bound is a bit more general. Like you can do some sort of Poincare series, and you can do this type of thing and say, okay, for the lower bound, I can get this. No. It can be very close to zero. That's what we do. Because the Schottky example can go very close to zero. But you get a lower bound in terms of some series depending on your group. But probably I would have time. Everything takes quite long. But just being able to say this would be, I'd be happy. So my question was, and this seems hard. Yes. No. So overall the M, which you're considering, of the dimension of the measure on the place of flag equal to the Hausdorff dimension. This seems well hard. I would say it seems hard. But first we punted that there's some measures that are well known, higher rate, Patterson-Sullivan measures of Kant, and that would work. But then but I think we don't know. But something happened during this conference, which is amazing, and I'm very happy. So there was already people working. Then we need plan. And they have a proof that the Hausdorff dimension. We don't know. We don't need to know what the right hand term the right is, but it's less than or equal to the Lyapunov dimension, which François talked a little bit about. But I don't care if you all remember what it is. I just want to say that this measure, or maybe it should be a rho. Okay, should be a rho with lower mu, I guess. And that suffices. That suffices for it. An amazing theorem, in my opinion, even if I say so myself. We're happy with this theorem. So the theorem, what it says is that for all rho from gamma to SL3, you can do it for SL4, 5, etc. You can also then the Hausdorff dimension of the limit set is at most 2.5. You can't get up to dimension 3, which is the full dimension of the black space, with an also representation. Limit sets, an also representation. Yeah, sorry, thank you. Thank you. Beautiful chalks. Okay. So the mu they consider have finite support, so they're in a nice context for the upper dimension. So we get this theorem, which for me is like, what is it? How can this be possible that we get this theorem? And so the first, I should say a few things that make this theorem unexpected. The first one is that it's really, really, really false for SL2R. Super false. You can do this. Yes, you have a lower bound. So the super dimension of the integral less than or equal to the upper bound. That's what you always get. It's the main use of that dimensions to lower bound. It's one of the popular uses of instructional measures for which you know that dimensions to lower bound than the next before. And here your upper bound, right? With the more extreme. And there is some reason to believe that it wouldn't be true, because there are some examples of conjugates or free, where when you do linear measures for the you don't get that's the final example. So my remarks are first of all, first remark, it's false. In SL2R and rank groups of rank 1. You can make these Cantor sets for the Schottky groups approach the dimension of one to one. It's not a big deal. And so what's the moral? The idea? Well, the idea is that gamma is hyperbolic. Again, really nice result by Borchi. And SL3R, where it's symmetric space. No, so gamma doesn't fit. No. Whatever that means. But so you would get, for example, I learned of a really nice argument. People know that you can't get gamma, the image of gamma, to be co-compact. That's impossible. You can't get the limit set to be the entire space of black. Because of the general position property, this I learned from the old Generalities, that because of the general position property, for each plane, there's at most one line that makes the flag belong to the limit. So at most, it's like some sort of section of one of the flag over there. But the section can have large dimensions, like a graph. But no, it doesn't. So I like this one. Yeah. So if I want to say something else, 10, 15 minutes, so probably not. Does anyone have any questions? So, fine. Thank you. So you have to use the construction, you can do on the surface map. And I don't know what is possible to get something about. I think that you can get. So one thing that happens is that anytime you have a final up of the plane, to put them into R3, making them act like they're trying to make a default one, plane parallel. So if you do like an IFS where the dimension of the set is very close to 2, you're already getting dimension close to 2 on the line. And then you just need like the stable subspaces not to line up too much. So it seems like you should be able to get more than 2 lines. I don't know, but for this, to me, it seems false. So like, when you look at this is not. I messed up somewhere. It's false. It's so false. Yeah. Yeah, so yeah, I would try doing IFS in the plane and then perturbing a bit, and I think you can get more than 2, but I don't know how to do that. And also, those are only semis, so it's also not an exam. So my answer would be I don't know. That's a good question. You can answer.